So everyone, having some technical difficulties. We'll try to set it up on this entire computer as well, but for now, you guys just temporarily just tune in like on your laptop, on your phone.
Yeah, we've got the live stream going, but this thing doesn't want to budge.
Isn't showing the laptop screen. Yeah. So if possible, you guys just hop onto YouTube now temporarily as well. Sorry about that. We should have emailed you the link to the video of emails.
And I'm going to say complex analysis, but then also key Magenis, educational psychology. So I heard it's like very easy, but it's an essay.
Just go through this. If there's any point, because like they're going to be watching the live stream, right?
Like I heard.
Yeah.
You go through because it's delay as well. Right?
Yeah, that's what I'm thinking.
It's like one of those subjects with marked 2 for attendance and what's the worst like? Which one?
Participation.
Yeah, participation. That's actually awful, but yeah, Fred's not good at that too.
I haven't gotten a single one.
I haven't
since
got to
has it started.
I think go in Fred.
Yeah, I've just gone live already.
So do I just?
You want to show you?
Do I go through the first slide or not?
No, I can just go into the content.
Basically, he was like, he didn't focus on any of the content, he was just doing his own thing. And when I say his own thing, it's like, I don't understand. So he was like, looking at how the real numbers are constructed. Literally no relevance to the course. It's like, every time I go to the training, get
Working. Oh, is it clear?
I can't, like, this is not helping me. Yeah, because I don't know, I didn't know what else to do, and I was like, and I talked to the guy who did educational psych, he's like, yeah, you should get a good mark here. If you really wanted a web booster, I was pretty sure Bruce told me that personal finance is the best web booster.
Wait, can you guys see the live?
You submit a budget. You submit a budget.
It's a bit of the
It's funny because Bruce does not need
Everything's
a web booster. Yeah.
Wait, I'm a bit sus though, because like he had a 98 well last time, and then 98 this time as well on LinkedIn. So does that mean he got exactly 98?
Maybe he didn't.
Maybe
Good? Alrighty, sorry for the delay, but we're about to start now. So thank you all for coming to the 1231/1241 revision seminar. Part 1 is today we're going to be presenting calculus, and it's presented by me, Fred, and Michael.
yeah. Hey guys.
So, alright, first topic we're looking at is functions of several variables. So functions of several variables. If we think about single variable, we just have like some f, like y in terms of x. But if we have two variables, we have f, x, y as a function of two variables. And to find the rate of change with respect to x or y, we need partial differentiation. And that involves just differing with one variable and treating the others as constants. So using the example above, if we have f, xy equals x cubed plus xy plus y cubed, if we diff that function with respect to x, so this x cubed here turns into 3x squared, and if we diff this xy, since y is a constant, we just get the y. And if we diff the y cubed with respect to x, we just get 0 since it's treated as a constant. And that's the same as if we diff with respect to y, we treat x as a constant. All right, so let's have a look at the mixed derivative theorem. It basically says that if let f be a function of two variables, and if f and all of its first order and second order derivatives are continuous, then if we take the partial derivative with respect to y, then with to x, we can actually swap it around. So we first take the derivative with respect to x, then y. Okay. Example that it comes into handy is if we have f of xy equals x squared y squared plus this monstrous expression involving y, and we're asked to find the partial derivative with respect to y, then x. So this thing here, we want to first diff with respect to y, then x. But if you think about it, we don't really want to be diffing that huge chunk with respect to y. So that's where the mixed derivative theorem comes in. So it says that we can actually diff it with respect to x, then diff it with respect to y. And yeah, that's exactly what it says here. And if we diff it with respect to x, since the whole of the second expression is just in terms of y, we can just throw that away since it's just a constant. And when we diff it with respect to y, we end up with 4xy. Okay. Now, moving on to tangent planes to surfaces. So if we have a function of the form f x, y, z equals 0, then the normal vector at the point P is given by this vector over here, where each one, so f subscript x, that just means the partial f partial x. And same for f subscript y and f subscript z. And using the point normal representation of the plane, we can actually find the tangent plane given by this equation. And a little intuition behind this is if we have a plane and we have the normal vector to the plane, and since the normal vector is perpendicular to the plane, if we take the dot product between the normal and any vector that lies on the plane, that should equal 0. And that's where we get the n dot with x minus p equals 0. All right. So question here, surface S in 3D dimension has z equals 3xy squared. The point P, 1, 2, 12 is a point on the surface S. And part A, we want to find the normal vector to S at the point P. So firstly, we have f x, y, z equals 3xy squared minus z equals 0. And recall the normal vector n equals these partial derivatives. So computing this normal vector, we first want to differentiate this with respect to x, and that results in 3y squared. Then diff with respect to y. So this is f subscript x, f subscript y, and we get 6xy. And if we diff this minus z, we should get minus 1. Okay. And that's going to be our general normal vector to the surface. But then if we evaluate it at the point P 1 to 12, we just plug those points in and we get our normal vector equals 12, 12 minus 1. All right, so for point B, to find the Cartesian equation for the tangent plane, we go back to the point normal form of the tangent plane, n dotted with x minus p equals 0. So we have found our normal vector from part A. We just dot that with this general vector. And don't forget your dot product expression. So we just
Okay, that works.
Oh, all right. We're back in business. So the screen is actually back, so you guys can just follow along the screen if it's easier for you. But yeah, so expanding this dot product, we get this equation of a plane: 12x plus 12y minus z equals 24. Right. So moving on to our total differential approximation. If we have some change in x and some change in y, the total change in f is actually dependent on the rate of change of f with respect to x, multiplied by how much it changes in x, added on with the rate of change of f with respect to y multiplied by the rate of change of y. Okay, that gives us our total differential approximation. And we can also use this to find the upper bound for the error in the approximation. Just take the absolute value on both sides and apply the triangle inequality, and that gives us the upper bound for the error, or like the maximum error that we get. Okay. So example here, we have an area of a rectangle with length x with y, and that's given as a equals x, y. And the question is, use the total differential approximation for a as a function of x and y to estimate the percentage increase when x increases by 5%, y decreases by 6%. And recall the differential approximation given by this formula. So notice that we're given that x increases by 5%, and that generates us the delta x equals 0.05x. But the second part is, be a little careful. This time is y decreases by 6%, and when we have decrease, we're going to have the minus sign to represent that it's decreasing. And the partial derivatives are pretty simple. They're given by y and x over here. So plugging this into our formula, we get that the change in A is equal to minus 0.01A, and that represents a 1% decrease in area. All right? And that gives us a way of applying the total differential approximation. So for chain rules, suppose that we have a function f(x) such that x is in terms of another variable t, and so is y. Then the chain rule states that we have this formula to compute df on dt. And another way to think about this is through the chain rule diagram. All right, so firstly, list out the variables that f is in terms of, and that's given by x and y. And then x and y are both in terms of t. Basically, think about this chain rule as how many ways can I get from f to t? Well, firstly, I can go from f to x, then x to t, and that gives us this first expression over here. All right? But I can also go from f to y and y to t, and that gives us the second expression. And that's an intuitive way of thinking about the chain rule when dealing with multivariable functions. So, now instead of having just x and y in terms of one variable t, this time we have x and y in terms of two variables s and t. But it's not too big of a deal. If we just redraw our diagram, our chain rule diagram, we get, and consider like the amount of ways we can traverse from f to s and f to t, we get this expression here. So if we look at, so partial f, partial t, so notice that we can go from f to x, then x to t, that's one path. We can also go from f to y and y to t. And notice that this time we actually use delta f on delta t rather than df on dt. The reason is because we end up, in the last step, we end up with two variables, s and t. And when we have like multi-variables, we want to use partial derivatives rather than just our single variable derivatives. Okay. So let's move on. Chain rules part 3. Now suppose we have this case where we have f in terms of u, but u is in terms of two variables x and y. Again, just draw out your chain rule diagram and you can easily compute your partial derivatives. And that gives us these chain rules. Again, we're going from f to u and u to x, and that gets us the partial f, partial x. Going from f to u and f to y, that gives us partial f, partial y. Now, in this monstrous case where we have like like 6 variables. Computing the derivative df on du is this monstrous expression over here. But just following again with your diagram, it should make it a lot easier. Again, it's just considering the number of paths we can take from f to u. So here's one path. Here's another path. We can go from x to t to u, and etc. We just add those paths together to get our final chain rule. Yeah, so we have example here. We have z in terms of 3 variables, a squared, b cubed, and plus c to the power 4, where a, b, and c are given by these functions in terms of u, v, w. And firstly, we want to find the partial derivative of z with respect to u at the point 1, 0, 1. Now, we have z in terms of abc and abc each in terms of u. So again, we can draw out our diagram. So we have z goes to a, goes to b, goes to c, and each of these, they go to u. Now, there are more variables, v and w, but we're only considering the partial z, partial u. So we don't really have to consider the other 2 variables, v and w. And again, we're considering the number of ways we can go from z to u. And that's going to be given by this formula over here, using our diagram. So, given that z equals a squared plus b cubed plus c to the power 4, these partial derivatives are pretty simple. We get 2a, 3b squared, and 4c cubed. Now, we also have a, b, and c in terms of these 3 variables u, v, w, and the partial a, partial u is equal 1, and same with the rest of these variables, b and c. They're fairly easy to compute. Now, this results in our partial z, partial u equals, if we just plug everything in, we get 2a plus 3b squared plus 4c cubed times v times w. We know the point P, v, u, v, w was, I believe, 1, 0, 1. Now, question, how do we find these other variables a, b, and c? Who knows how we can find those? Yo. Yeah. Yeah, we can use our expressions, right? If we go back to our previous slide, we're given to us in the question that a equals u minus v plus w, b is this, and c is u, v, w. We just plug those numbers in, and we get 2, 0, 0. So in the end, just plug a, b, c, u, v, w into our chain rule, and we get our final answer equals 4. All right? So, all right, moving on. That's the end of chapter 1. Let's move on to chapter 2, integration techniques. The first case we're dealing with is these trigonometric integrals where we have powers of sine and cosine. And case 1 is when n is odd. And when n is odd, we can actually split this integral into cos n minus 1x times cos x dx. And then we use the u sub u equals sine x. That way, this part here becomes our du. And then this cos, since n minus 1 is even, we can actually convert it into 1 minus sine squared. Case 2 is very similar. This time is when we're considering when m is even. Similarly, when n is even, we can split out the sine. And then we use the sub u equals cos x. That way, this part here, sine x dx, becomes minus du. And then again, we know that m minus 1 is going to be even, so we can convert that into a cos. And the third case is the most annoying, is when we have both m and n, they're both even. And the way we compute this integral is we have to use this double angle identity, these ones over here. These ones over here, to reduce the powers down to something that we can easily compute. So say like power 0 or power 1. So we reduce it down so we can easily compute these integrals. Now, example is if we have integrate sine to power 4, and that was exactly the case for our third case where we have even. So we're going to use our double angle identities, and sine squared equals 1 minus cos 2x divided by 2. But since we're dealing with sine to the power 4, we square the whole expression, and we expand it out. All right, let's expand everything out. But now you want to notice that we have this extra cos squared 2x at the end. And since we have sort of like an even power again, we want to apply that same trick where we reduce the power down by using our double angle formula. And that's what we get over here. It turns into 1 plus cos 4x divided by 8. And after simplifying this expression, we're basically integrating this easy expression that we know we can easily integrate. So the first one just becomes 3x on 8. Cos goes to sine. Same cos goes to sine. And then we add a plus c at the end. And that gives us a way of integrating this sine to the power 4. First, just by reducing the power down using the double angle identities. Alrighty, next up is if we have these kind of integrals, we have products. Case 1 is if we have integrating sine cos. Basically, what we want to do is use the product to sum identity. That way, we can easily compute sums of trig identities, just integrate each one individually. Whereas if we're given a product, we don't really know. So these products to sums identities, they help out really nicely. Case 2 is if we have cos. That's the same, just apply products to sums again, and same for sine. Just one thing to clarify is that we use these when we have m not being equal to plus minus n. If we have m equals plus minus n, then we're essentially just integrating like cos squared and sine squared, and we don't want to be using these products to sums to integrate those. So example here, we have integrate sine 3x cos 2x. So just apply your product to sums to integrate this. We get half of sine 5x plus sine x. And these you can easily integrate. Sine goes to cos, and they're a sum, so you can easily break them up. And you should get minus cos 5x on 10 minus cos x on 2 plus c. Other important identities. These ones you're going to need when we're having integrals of like tan and sec. These three identities you're going to use in your integrals. So let's have a look at an example. Is if we have integrate sec to the power 4 times tan x. Now, the first thing that you want to realize is we have the derivative of sec x equals sec tan. And in our question here, we have just a single tan. But that isn't a problem, because we can actually split this up into sec cubed times sec x tan x. Right? We can actually split one up by pulling a sec out of the sec to the power 4. And then what this results in, we get this expression over here, where we let u equals sec x, that way du equals sec x tan x dx. And then this part here just becomes our du. This part here becomes u cubed. And then integrating u cubed is just integrating a power function. That is really easy. We get u to the power 4 on 4 plus c, which is sec to the power 4 on 4 plus c. All right. Now, moving on, we have a reduction formula question. Now, given some general formula for an integral, show that this formula, reduction formula, holds. You look at the question and you're trying to relate in with in plus 1. But one thing that you want to notice is the way to get the n plus 1 is if we differentiate the fraction that we have, we get something like minus 2nx over 1 plus x squared to the power n plus 1. And this n plus 1 here is, that's going to be where the in plus 1 comes from. So when we're trying to diff, we're thinking about integration by parts. A brief recap on integration by parts is if we have integrate u dv, that's going to be uv minus integrate v du. How I like to think about this is just get the u, chuck it out front, get the v, chuck it out the front, and then for the second integral, just swap the u's and the v's, so the v's come outside, and then the u goes inside the d. All right, that's essentially integration by parts. And yeah, applying the integration by parts, we get something like this. So again, this comes outside, the x comes on the outside. And then we swap, remember we swap the u's and the v's. So inside this integral, the x comes outside, this fraction goes inside the d. All right, just swapping it for the integrals. Now, firstly, just plugging our bounds in for the first part, and the second part, which is our integral, we just firstly simplify our integral by differentiating that expression over there. And yeah, so let's further simplify. Oopsies, my bad. Let me scroll. Alrighty, so simplify that integral, and we end up with integrating x squared on 1 plus x squared to the power n plus 1. Now, one thing that you want to notice is that in the bottom we have 1 plus x squared, but in the top we only have a single x squared. A lot of times in integration, we want to be like forcing numbers in and then removing them after. And that's exactly what we want here. To make it look like the bottom, we just force a 1 plus x squared in the top. But we can't just leave it like 1 plus x squared. That's just going to completely change the integral. So we have to subtract 1 after, at the end. So we get something like this. Okay. And there we have it. We have 1 plus x squared minus 1 at the very top. And that simplifies down to, if we split the fraction at the top, we get this expression over here. And notice that this first integral here, this thing here, that becomes I of n. And notice that in the power for the second one, the power is n plus 1. So the second integral is going to be I of n plus 1. That's what we have over here. And then now, you want to see that we have in in terms of in and in plus 1. So the last step here is to just make in plus 1 the subject, and that way we get our reduction formula. So just make 2n in plus 1 the subject, and then move the 2n down. and we get in plus 1 in terms of I of n. Alrighty, moving on to some trig and hyperbolic substitutions. Basically, we're given some integral factor, and what this integral factor means is pretty much every time you see like these kind of expressions like root a squared minus x squared, or root a squared plus x squared, you want to be thinking about trig and hyperbolic substitutions. Whichever one you go for is personal preference. But yeah, whichever one you're more comfortable with, stick with that. I like to go with just regular trig substitutions, especially for indefinite integrals. Alrighty, using trig subs over here, we have an example. Find this integral 1 on x times square root x squared minus 1. Now, the first thing that you want to realize is this x squared minus 1 inside a square root. And that's going to normally tell you that you want to use a trig sub or a hyperbolic trig sub. And if you go with a trig sub, the identity that you're aiming for is sec squared minus 1 is tan squared. All right, so that's what you're aiming to use. And so here, we want to use our sub x equals sec theta. And that's what we let over here. X equals sec theta, dx equals sec tan. So just plug these values in, and notice that firstly, the secs cancelled out. And then sec squared minus 1 inside the root becomes a tan squared. That simplifies all the way down to just integrating 1, which is really easy to integrate. We get theta plus c. But this is doing indefinite integrals. We have to convert our theta back into x. And our original sub was x equals sec theta. Now you can say that theta equals sec inverse x, but I don't really like using sec inverse. So instead we can write it in terms of cos inverse. So if we have x equals sec theta, then cos theta is going to equal 1 on x, since they're reciprocals of each other. And we have theta equals cos inverse 1 on x. All right, that's going to get us the answer. All right, so a bit of partial fractions. In this question, they've given us the partial fractions split out, and essentially we have to use that to find the integral. So, using the information that they gave us, we're going to split the fraction into 2 separate fractions. This first fraction is really easy to integrate. It's just integrating 2 on x plus 3. It turns into an ln. But this second fraction here, we don't really know what to do. And you look at it, we have a linear term at the top and a quadratic at the bottom. And every time we have one of these kind of integrals, we first want to look at, analyze the derivative of the bottom. So if we diff the bottom, we get a 2x. And we're going to compare this diff with our numerator. And in the numerator, we have x minus 5. So what we can do is, to get our 2x involved, we can split the numerator out into x and then minus 5 as 2 separate fractions. And then that way, we know that this first one goes to an ln. This second one, since the top is in the form of the diff of the bottom, that would also go to an ln. And the third one here, that would go to an inverse tan. Or not inverse tan x, but some inverse tan. All right, and we get our final answer over here. And notice that I left out the absolute value in here, since we know that x squared plus 2 is always going to be positive, and that gives you the final answer. All right, next topic is going to be ODEs, and I'm going to be handing over to Michael. and we'll be covering the next two topics.
So hey guys, I'm going to be doing ODEs and ODEs and Taylor series and sequences. Okay, so there's 5 different types of ODEs, and I'm going to be going through what each one is and an example from a past paper for each type of ODE. So here are the 5: separable first order linear, exact second order linear, and for second order linear we have 2 cases. We have the homogeneous and non-homogeneous. Okay, so a separable ODE is one where you can essentially split the equation into 2 halves, where all your y's are on the left-hand side and your x's are on the right-hand side. And I'm sure all of you have seen many of these questions before. An example of a separable ODE is dy on dx equals 4x to the 4 y squared. And it's separable because we can get the y's on the left-hand side by dividing both sides by y squared. And then we can also divide both sides by and then we can also bring this dx onto the right-hand side so that all of our x's are on the right. And so we can see it's separable. And all we have to do from here to solve the differential equation is essentially just chuck an integral sign on both sides and solve. And don't forget about the constant of integration, which you'll have to put on only one of the sides. Okay, so something new is, what if we have an ODE of the form dy on dx is a function of the quotient y on x? Well, we can make the sub y equals xv, where y and v are obviously functions of x, and this should transform this ODE into a separable ODE, which we can easily solve. Now, here's an example of one. So we have dy on dx equals xy plus y squared, all on x squared. Now, we can see that this is actually, the thing on the right is a function of y on x, and we can see this by splitting the quotient into 2 separate fractions. So if we do that, the first term is going to be xy on x squared, and that should just give us y on x, and then plus, and then y squared on x squared, which is the quotient y on x, all squared. So we can see this is clearly a function of y on x, and so what we're going to want to do is make the sub y equals xv. And you'll see why in a second. So given y equals xv, well, what's dy on dx? Well, dy on dx is just the derivative with respect to x of xv, and we can simplify this using product rule. So if we differentiate the first factor x, we're just left with 1, and then so that it turns into v. Sorry. Okay, so that just becomes v, and if we differentiate the second factor v, we'll note that that's a function of x. So we're going to write that as dv on dx, and then we're left with the x in front of that as its coefficient. And so that's our dy on dx. Now, notice that we can simply replace what we just got with the left-hand side of the ODE, and that becomes, like we just said, v plus x dv on dx. And the right-hand side is y on x, which is v, because we can rearrange our substitution so that y on x is v. So the right-hand side of the ODE simply just becomes v plus y on x squared, which is v squared. Okay. Okay, so we have v plus x dv on dx equals v plus v squared. And notice that the v's can obviously cancel out, and so we're just left with the separable ODE x dv on dx equals v squared. Now we know how to solve this. We rearrange so all the v's are on the left, and all of the x's are on the right. And then we chuck an integral sign on both sides, integrate. Left-hand side becomes negative 1 on v. The right-hand side, when we integrate 1 on x, becomes the natural log of the absolute value of x, plus c, since we need a constant of integration on either side I like to put my constant of integration on the side of x. And don't forget the absolute value sign, otherwise you risk losing a mark. So only here, that is when we replace v with y on x. And doing that, we get negative x on y on the left, and our right-hand side stays the same. It's just ln absolute value of x plus c. And that gives us, after rearranging, we can isolate y, and we get y is negative x on ln absolute value of x plus c. Okay. So the next type of ODE is the first order linear. Now, first order linear ODE is one expressed in the form dy on dx plus a function of x times y equals another function of x. Okay? And note that the form that we want it in has a monic dy on dx. So the coefficient of dy on dx is monic. And this allows us to solve these equations. So for example, if we look at this equation, 2dy on dx plus 4x cubed y equals 3x, well, if we divide both sides by 2, that's how we can get the monic dy on dx. And we can see that this is clearly a linear ODE, since our coefficient of y is a function of x, and the thing on the right-hand side is a function of x. Now the method to solve this, well, the first step is to get it in this form that was in the last slide. And notice that this form, I'm going to keep stressing it, has a monic dy on dx. Because it has to be monic in order for us to use this method. So once we've gotten the ODE in that form, we want to calculate the integrating factor, which is given by e to the integral of f of x dx, where f of x is the coefficient of y. And note that when we integrate f of x as a part of the exponent, we're not worrying about what the constant of integration is. So once we've got the integrating factor, we want to multiply both hand sides of the original ODE by that integrating factor, h of x. And the only thing important from here is that the right-hand side it's not g of x anymore. It's now h of x times g of x. And because of the product rule, we can actually write this entire left-hand side as simply just the derivative with respect to x of hy. Now, this is the important step. And from here, we can integrate both sides. And notice that the integral cancels out with the d on dx. So these two cancel out. We're just left with h of x times y is equal to the integral of g of x h of x with respect to x. And all we want to do from here is isolate y by dividing both sides by h of x. So we're going to end up getting something like y equals the integral of g h dx all on h. So that's going to be our method. Now on to one of the questions. So solve the IVP defined between 0 and 1 for x, and it's that first order ODE. And they're giving us an initial condition where y, when x is 0, is equal to 1. And we're going to be using this initial condition towards the end of our solution. So notice that it's already monic in dy and dx. So that's the first step done. We've already got it in the form we want. Now, the second step was to calculate the integrating factor, which is e to the integral of f of x, where f of x is the coefficient of y. So notice that f of x, in this case, is equal to negative x all on 1 minus x squared. Simply just the coefficient of y. And so our integrating factor, h of x, is going to be e, so I'm going to write it as x, because it's a large expression, of the integral of negative x on 1 minus x squared dx, close bracket, and we're not going to worry about the constant of integration for this integral. Okay, now doing that, it should be a simple integral. So using standard methods, we want the numerator to be the derivative of the denominator so that we can write it as a natural log. And the way we do that is we factor out a half, and so the numerator now becomes negative 2x, which is the derivative of the denominator. So from here, when we integrate, we simply just have a logarithm of the denominator. And notice that, actually, could someone explain to me why I left out the absolute value inside the logarithm? No? That's all right. Yeah, so the reason why I did that is because in the question it says x is greater than or equal to 0, but strictly less than 1. And so we know x squared is going to have the same inequality. And so 1 minus x squared will be positive. So it's fine if we leave out the absolute value of the input of the logarithm. And note that we can write a half log 1 minus x squared as log of the square root of 1 minus x squared using our logarithm laws. And so when we have e to the power of that, the e and the log inverse functions, they cancel out, and we're just left with the input of the logarithm, which is the square root of 1 minus x squared. Yeah. Is there a reason why we use log? Like, are you asking like natural log or? What? Oh, so you can use the same notation. So log and ln mean the same thing. You can use that notation for the natural log. Okay? Maybe it would have been better to write ln just to be more clear, but we can use both those notations to represent the natural log. Okay? Cool. So we've calculated the integrating factor now, and that was our second step. Now the third step was to multiply both sides of the equation by h of x, which we said was the square root of 1 minus x squared. And in the last step, we said that we could write the left-hand side as the derivative with respect to x of h of x, the integrating factor, times y. So that's what we get after simplifying that. And on the right-hand side, remember, it wasn't g of x anymore. It was h of x, g of x. And we could see in the question what g of x was. G of x was 2 on 1 minus x squared, which means our h of x, g of x, is 2 times h of x, which is the square root of 1 minus x squared, all on 1 minus x squared. And we can simplify that to 2 on the square root of 1 minus x squared. Okay, so that's what I have here. And from here, we're just going to integrate both sides with respect to x. Note that the d on dx over here cancels out with the integral, so we're just left with square root of 1 minus x squared times y. And the right-hand side, using inverse sine trig, inverse sine integration, we're just left with 2 times inverse sine of x plus c. And to eliminate the constant of integration, we're just going to substitute in our initial conditions, which was when x is 0, y is 1. We sub that in, we end up getting c equals 1. And so this is actually 1. And rearranging for y, we're left with our final solution. Y is 2 times inverse sine of x plus 1, all on the square root of 1 minus x squared. Any questions with that? Cool. Okay, so the third type, exact ODEs. So exact ODEs are of the form a function of x and y on its own, plus a function of x and y multiplied by dy and dx, so it's the coefficient of dy and dx, equals 0. And we call this equation exact if and only if the partial f partial y is equal to partial g partial x. Now the reasoning behind this is quite complicated and is related to product rule of multivariable calculus, but just know that this has to be true in order for the equation to be exact. So in past papers or in exams, they usually show that this equation is exact. If we show that it's not exact, well then we don't have the methods to continue on with the question and solve it. So it must be exact in order for us to be able to solve it. So there's good chances that in the exam the equation will be exact. So you're looking for an expression like this. Now in the case it is exact, which should be most of the time, the solution to the ODE is given by some function h in terms of x and y is equal to a constant. And the only thing we have to do is find that h. Now, that h needs to satisfy two conditions. Partial h, partial x is equal to our function f in the original ODE, and partial h, partial y is equal to g in the original ODE. Now, these three things that I'm surrounding in the square box are just three things you're going to have to memorize for exact ODEs. So an example from a past paper, show that that equation is exact. So that's going to be our first step. And then find the general solution. So we said that it's exact if partial f partial y is equal to partial g partial x. So partial f partial y is going to be, sorry, I'll mention that f is the one that's not the coefficient of dy and dx, whereas g is the one that's the coefficient of dy and dx. So partial f partial y is just going to be equal to sec squared y. The 2x goes to 0 since we're differentiating with respect to y only and treating x as a constant. And partial g partial x is equal to sec squared y. And the negative 2y goes to 0 since we're treating that as a constant. So note that partial f partial y is equal to partial g partial x. And so the equation is exact. Now we're asked to find the general solution. Okay, so once we've shown it's exact, we know that there exists an h such that partial h partial x is equal to f, and partial h partial y is equal to g. Now I've labeled those two equations 1 and 2. And how we're going to find h, we're going to integrate equation 1, both sides, with respect to x, and we're going to be treating y as a constant. And I'll explain why in a second. So integrating both sides with respect to x, left-hand side simply just becomes h, because the partial derivative gets cancelled out. The right-hand side, well, we're treating y as a constant, which means our tan y is going to be a constant, and so we're left with x tan y, and obviously the 2x becomes x squared. So x tan y minus x squared. And then we're going to have that constant of integration, but that constant of integration is allowed to be a function of y. And the reason why is once we differentiate h with respect to x, all of the terms in y are going to go to 0. Okay? So there could actually be a hidden term in terms of y that when we differentiate h with respect to x, it just goes to 0, and so it's hidden essentially. So this constant of integration is allowed to be a function of y. Now, if we differentiate this equation, both sides, with respect to y, we have partial h partial y is equal to x tan y becomes x sec squared y, since x is now the constant. And then the minus x squared goes to 0, since it's a constant. And then plus, the constant in terms of y, we can actually differentiate it, because it doesn't necessarily have to go to 0, since it could have that hidden y term. So we're left with delta h on delta y is x sec squared y plus c1 dash of y. And we're going to label that equation 3. And now we have two equations for partial h partial y. We have equation 2 and equation 3. And comparing these two equations, the x sec squared y matches up. We also need the negative 2y and the c1 dash y to match up as well. So we're going to want c1 dash of y to be equal to negative 2y. Now integrating both sides with respect to y, we're just left with c1 of y. The right-hand side becomes negative y squared plus a constant of integration. And what we're going to do is we're going to ignore that constant of integration, sub in our value of c1 of y into this equation here, and we're left with x tan y, so that stays the same, minus x squared. And now we know that our c1 of y was minus y squared. So we now have our h, and all we're going to do in our final line is just let h equal a constant, capital C, and that's our solution. Does anyone have any questions with that? Cool, pretty straightforward stuff. Now on to second order ODEs. So second order homogeneous ODE is where you have y dash dash plus a times y plus ay dash plus by is equal to 0. Now the fact that the right hand side is 0 makes this equation homogeneous, and a and b are obviously constants. Now what we're going to do is, to solve these equations, is we're going to solve the characteristic equation first. And the characteristic equation is a quadratic in terms of some parameter lambda, and it's going to be of very similar form to the ODE. So the y dash dash becomes lambda squared, the a y dash becomes a lambda, and the by becomes b. And this is the quadratic characteristic equation that we're going to solve. And once we solve that quadratic in terms of lambda, if we have two distinct real roots, lambda 1 and lambda 2, then our solution is going to be of this form. Y is ae to the lambda 1x plus be to the lambda 2x. Now the second case is when lambda is a repeated root. So in this case, y is going to be ae to the lambda 1x plus b, and then there's a little x, a lot of students forget about, including myself, bx e to the lambda 1x. And now if both our solutions were complex, and so therefore they're a complex conjugate pair, since it's a real polynomial, a real quadratic, then our solution is going to be of this form. And the real part of our solution for lambda is associated with the exponent at the front, and our imaginary part, beta, is associated with the trig, functions, cos and sine. And this is the form that you're going to have to memorize. Make sure you don't screw it up in the exam. Now, just a quick example. Write down the general solution to this equation, and we're given an initial condition. So all we're doing is solving the characteristic equation, which would be lambda squared plus 4 lambda plus 4 equals 0. So with the 4s corresponding to the 4s in the ODE. Now, we can write the left-hand side as lambda plus 2 all squared is equal to 0. So lambda is equal to negative 2. And so we have a repeated root in this case, which means we know our solution is going to be of the form, this one. Y is equal to ae to the lambda x plus bx e to the lambda x. And so therefore, it'll be ae to the negative 2x plus bx, since we have the repeated root, e to the negative 2x. Okay, and we're given the initial condition. So when x is 0, y is 0. And summing these values in, 0 is equal to ae to the 0 plus b times 0 e to the 0. And this term, with the b as the coefficient, becomes 0. So we're just left with 0 equals ae to the 0, which is a. So we know a is 0, and therefore our general solution, the ae to the negative 2x term, becomes 0, since a is 0, and we're just left with y is equal to the b term, bx e to the negative 2x. And that's our final solution to that. Does that one make sense? Cool. And then the last type is second order, but it's a non-homogeneous ODE. So the only difference between this one and homogeneous is that the right-hand side doesn't have to be 0. It's a function of x and not y. Okay. Now the method to solve this is we're first going to treat it as if it's a homogeneous equation. So we're going to pretend like the right-hand side is 0. We're then going to solve the equation using the method we just learned, and we're going to get our homogeneous solution. So that's going to be YH. Now, after finding the homogeneous solution, we're going to find a particular solution to the ODE. And I'll go through that in a second. But once we've found this particular solution, we found YP, and so our general solution to the original ODE is just going to be the sum of YH and YP. To find the particular solution, we're going to have to make a guess. And once we make that guess, which will be in the next slide, on how to make the guess, we're going to substitute it into the ODE, and we're going to equate both sides. So we're going to substitute it into this ODE and equate both sides to find unknown coefficients. Now, this is like a holy grail table of like how to make guesses for YP, and it's one that you're going to have to memorize, but the intuition behind it isn't actually too bad. So if our right-hand side is a polynomial of degree n, well, then our guess is also going to be a polynomial of degree n. For example, if our right-hand side was 7x, our guess would be a linear polynomial as well, and so we'd write it as ax. And then we'll obviously have to sub it into the ODE and find what A is by equating coefficients. If our right-hand side is a polynomial of degree n times e to the sx, then our right-hand side is going to be a polynomial times e to the sx. If our left-hand side is a polynomial times a trigonometric function like cos or sine, then our right-hand side is going to be the same thing. However, it's going to be the sum of a polynomial times cos plus a polynomial times sine. And this is the most complicated one, where we have a polynomial times an exponent times a trigonometric function, and the right-hand side is going to be the same thing, but it's going to include the cos and then added to the sine. So polynomial times exponent times the sum of the trigonometric functions. And just a quick note, if the right-hand side is a constant, this is actually a polynomial of degree 0, and so our guess is also going to be a polynomial of degree 0, so it would just be the constant a. Now, this was one of the last questions of a past paper, a 1251 past paper. Solve the following IVP. So what we're going to do is we're going to first treat it as if it's homogeneous. So I'll represent that by HE. It's going to be y dash dash minus 5y dash plus 6y is equal to 0. So that's a homogeneous version of the equation. And how are we going to solve that? We're going to solve the characteristic equation, which is the quadratic lambda squared minus 5 lambda plus 6 is equal to 0. Factorize the left-hand side, lambda minus 3, lambda minus 2 equals 0. And so lambda is 3, or lambda is 2. And so these are two distinct roots. So we're going to be looking at that first case for the homogeneous solution, where our solution would be of the form y is ae to the 3x plus be to the 2x. So that's going to be our general solution for the homogeneous equation. So that's our YH. Okay, so that's the first step done. Now we're going to look for a particular solution. So we can see that the right-hand side is 10e to the 2x. Now it would make sense to make a guess for the particular solution. Yp is equal to a polynomial of the same degree, which is just a constant, times e to the 2x, using our table of guesses. However, one important thing to note is we don't want any of our particular solution to overlap with our homogeneous solution. Now note that if we made this guess, if we made it a constant times e to the 2x, it would actually overlap with this part of the homogeneous solution. And therefore, it wouldn't be a good guess to make. So what we're going to do, and this is a common trick, you're going to multiply that guess that you wanted to make but didn't actually end up working by x. So our particular solution guess is actually going to be ax e to the 2x. So that's going to be our guess. Okay. And instead of a, I just used the capital C for the constant. So that's our guess. And we're going to differentiate it once and twice to find respective yp dash and yp double dash. We're going to sub it into our original ODE. So this one here. And we're going to equate coefficients. Now these are pretty standard calculations. If you wanted to find the derivatives, we're going to be using product rule. And then once we sub it in, standard calculations where we're just collecting like terms really, and then equating coefficients, we end up getting negative c e to the 2x is 10 e to the 2x, so c is going to be negative 10. And so if we sub in c equals negative 10 into our guess becomes yp is equal to negative 10 x e to the 2x. So we've got in our yh, we've got in our yp, and so our general solution to the ODE is the sum of the two, which was ae to the 2x plus be to the 3x minus 10x e to the 2x. Now we were given a bunch of initial conditions. I believe it was y of 0 is equal to 1, and y dash of 0 is equal to 1 as well. Now we're going to substitute in the x and y, respective x and y values. We're going to end up getting two simultaneous equations in terms of a and b. We get a plus b is 1, 2a plus 3b is 11. solve them simultaneously, and we get our values for A and B. And we're essentially subbing in the values of A and B that we just evaluated into our general solution. And we're left with the final solution. Y is negative 8 e to the 2x plus 9 e to the 3x minus 10x e to the 2x. Is there any questions with that? Okay. Now that concludes ODEs. Another type of ODE question, which they can often ask, is like an inflow, outflow question. So I guess if you have like any problems with that, you can ask after the seminar. Okay, so Taylor series. So definitions of sequences. So a sequence is a function with natural numbers as its domain and the real numbers as its codomain. And they have their own notation. It's got like the squiggly brackets around a subscript n. And if you see an infinity and an n equals 0 to the right of the second squiggly bracket, just know that it doesn't mean sum or series. It's actually referring to the infinite sequence. Now, they're always defined by some rule. For example, an equals n squared, or an equals an minus 1 plus an minus 2. So the sum of the two previous terms. And in this case, that would just be the Fibonacci sequence. So convergence and divergence. So a sequence can either converge or diverge. And it's convergent if it approaches some finite number L as n approaches infinity. And we can represent that as an equation, limit as n goes to infinity of a subscript n is equal to L. Now, if it's not convergent, it must be divergent. And also, we can examine the limiting behavior of a sequence by essentially letting the rule be some sort of function and then taking the limit of that function as n goes to infinity. And you'll see that the limiting behavior of the sequence is actually equal to the limiting behavior of that function of the rule the sequence takes. So for example, if an was equal to n squared, like in the previous side, we'd let it be a function, we'd let f of x be x squared, and then take the limit as x goes to infinity of that. And we can obviously see that a subscript n, the sequence, diverges. Now, quick question, determine whether the sequence that square root n squared plus 3n plus 3 minus n converges or diverges. And then if it converges, find its limit. Now, the trick with these is you often want to rationalize the numerator. So we'd multiply top and bottom by essentially its rational conjugate. So, the square root is going to stay the same. However, it's going to be a plus n instead of a minus n this time. So we can use the difference of two squares property to essentially eliminate the terms. So we're going to multiply the top and bottom by the root n squared plus 3n plus 3 plus n. So we're not changing the value of anything since that fraction is equivalent to 1. And rationalizing the numerator by the difference of two squares, the numerator becomes n squared plus 3n plus 3 minus n squared. N squared terms cancel out, and we're just left with the linear 3n plus 3, whereas the denominator doesn't change. And what we're going to do is we're going to take out an n from the denominator so that in the next step we can cancel out all of the n's. We can divide every single term on the numerator and denominator by n. So if we take out an n on the denominator, there's already an n here, so that's fine. So all we need to do is take out an n from the square root. And if we take out an n, we're essentially dividing each term inside of the square root by n squared. So we're going to be left with 1 plus 3 on n plus 3 on n squared in the square root. And now that we have n's essentially for every term, note that we can write 3 as 3n on n. We can divide every single term on the numerator and denominator by n. The 3n becomes a 3. The 3n on n becomes a 3 on n. The square root stays the same while the n goes away, and this n becomes 1. And now that we take the limit as n goes to infinity, all of the terms with an n or an n squared on the denominator approach 0. So this term goes to 0, this term goes to 0, this term goes to 0. We're just left with 3 on the square root of 1 plus 1, which is just 3 on 2. And so the sequence converges to 3 on 2. Make sense? Cool. So sequences, So essentially, we can use standard operations with sequences. So the sum of a sequence is a sequence of the sum. And also, if two sequences are convergent, then the limiting behavior, like the limit formulas or the limit laws, apply for the product and the quotient of the sequences. So the limit of an bn is equal to the limit of an times the limit of bn, and same follows for the quotient. However, note that these rules only apply if we know in advance that both of these sequences are convergent. Now, this is just order of growth. Something you don't have to memorize, but it could come up, it could pose useful in an exam. So essentially, log n grows faster than 1, n to the k grows faster than log n, c to the n, so now the index is n and not the base, grows faster than n to the k, n factorial grows faster than c to the n, and then n to the n grows the fastest. So you don't have to know this, but it could pose useful. Now the pinching theorem for sequences. So if we know in advance that a sequence Bn is sandwiched between An and Cn, well, if An and Cn both converge to the same value L, then we know Bn must also converge to L. And that makes sense, since the limit as n goes to infinity of An is equal to the limit as n goes to infinity of Cn. And since Bn is sandwiched in between those two values, Bn would have to be equal to both An and Cn, which is L. Another test for convergence. So this only applies to 1241 students. So we call a sequence monotonic if it is increasing, non-decreasing, decreasing, or non-increasing. It's a mouthful. But the way I like to remember it is there's no 2 points. There's no 2 points on the graph where the graph is increasing and decreasing. So you can't select 2 points where one of those points is increasing and the other point is decreasing. Its sequence is bounded above if there exists a number m such that all of the values in the sequence are less than or equal to m. That's pretty self-explanatory. And similarly, the sequence is bounded below if there exists a number m such that all of the values in the sequence are greater than or equal to that number. And if a sequence is both bounded and monotonic, then it converges. But remember, this only applies to 1241 students. And similarly, Suprema and Infima also only applies to 1241 students. So the Supremum is the least upper bound of a sequence. So it satisfies 2 conditions. Every single value in the sequence is less than or equal to that Supremum. So this is essentially just saying it's an upper bound from the previous slide. And the other condition is that it's the lowest upper bound. So if you select any other upper bound, then that upper bound that you just selected would be greater than or equal to the Supremum. And the infimum has the reverse characteristics. It's just the opposite. So instead of being the least upper bound, if you take like the opposite of each of those words, the greatest lower bound. And it's essentially the way I think of it is if you have a real number line and you have a sequence going from a sequence on this number line, the infimum is the very lowest the sequence goes, and the supremum is the very maximum. So your whole sequence is essentially sandwiched between these 2 values. And I'm not sure if there's any 1241 students here, but could someone tell me what the supremum and infimum of the set is? No? Yeah, Fred. Yep, supremum doesn't exist. Yeah, exactly. So 1 plus n squared all on n is strictly increasing. Every term is going to be strictly greater than the previous term. Now, what does that mean? It means that there is no supremum, because the sequence keeps getting bigger and bigger. It diverges to infinity, and so there is no maximum. So the supremum, or sup, does not exist. And the infimum, well, since the sequence is strictly increasing, it makes sense that we're going to get the lowest value of the sequence for the lowest value of n. And the lowest value for n is n equals 1. So if we substitute n equals 1 into the sequence, we should get the infimum is equal to 1 plus 1 squared, all on 1, which is 2. Cool. So infinite series, so essentially a partial sum just represents the sum of terms of a sequence up to n. So it's the sum of the first term, a subscript 0, with the second term, a subscript 1, all the way up to the nth term, a subscript n of a sequence, and we can represent that using sigma notation. Now, if the partial sum approaches some finite L, so essentially if the series converges, then we say it's summable. And if it doesn't converge, so if the series does not approach some finite number, well then, like we said before, it must diverge. Summable series. So if we know two series are summable in advance, we can just use standard operations. So essentially the sum of the series, the series of the sum is the sum of the series, and then the series of the scalar multiple is equal to the scalar multiple of the series. So these are just simple operations we can use with sigma notation. And just like note the terminology, sequences applies to, the term sequence applies to the set, so A0, A1, dot, 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 whereas the series actually means the sum of these values. Now, for finite sums, if we know two series are finite, if we know a series is finite and it converges, then the lower bound actually does not matter. Whatever the lower bound is, it's going to converge. So this is the first test we'll use. So the kth term test for divergence, or just the kth test. So if as k goes to infinity, the sequence value does not approach 0. So essentially, if you have a sequence and you have like 4, 2, 1, dot, 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 if the term does not approach 0 as k goes to infinity, then the series must diverge. And this makes sense intuitively, since if it doesn't approach 0, then it's going to be some non-zero value. And if you're going to keep adding it in an infinite series, your series will never converge. It will never terminate. So this kind of makes sense intuitively. And if we take the contrapositive of the statement, since we know this statement is true, the contrapositive of this will also be true. And I've just named the contrapositive below. It's the second statement. It's saying that if we know a series converges, that means the sequence approaches 0 as k goes to infinity. Now note that the opposite doesn't necessarily have to be true. The opposite would be if the sequence approaches 0, the series converges. That's not necessarily true. Comparison test. So it's similar to the pinching theorem. It's just applied to series. If we have 0 is less than or equal to sequence k is less than or equal to sequence bk, well, we can just sum this. So it becomes 0 is less than or equal to the sum of the sequence, or the series, is less than or equal to the sum of bk, which is the series of b. And this is essentially the pinching theorem. So if we know b, the series b converges, then the series a must also converge, since it's sandwiched between two finite numbers. And similarly, if a diverges, well then since the series b is greater than the series a, we know the series b must also diverge. And then p series, so p series is just a sum of reciprocals, where the reciprocal is taken to the power p. So this will only converge if p is greater than 1, and will diverge for all other values of p. And you can prove this using an integral test, but we won't do that today. Yep. So this is actually the last question of one of the 2018 1231 past paper. Now, it says, suppose that this series, A, is a convergent series, and all of the terms are positive. Now, part A is, state the limit as n goes to infinity of A subscript n. So it's the limiting value of the sequence. Now, could someone help me out with this one? Does anyone know what the limiting value of the sequence is? It's all right, I'll enter. The series is convergent, we know that. And so by the kth term test, we know that if the series is convergent, then the sequence must approach 0. So by the kth term test, we know that the limit as n goes to infinity of an equals 0. Part B, use the nth test or the kth test to show that this series diverges. Okay? Well, we know that the sequence approaches 0. Okay, so what about the limit as n goes to infinity of the natural log of a subscript n? Well, since the natural log is a continuous function, we can actually insert the limit inside of the input. So it becomes the limit as n goes to infinity of a subscript n. And from part A, we said that this value must be equal to 0. Otherwise, the series wouldn't converge. So this essentially approaches the natural log of 0. It'd be 0 plus, which approaches negative infinity. So we can see that looking at like the graph of sorry, that was a horrendous graph. The graph of the natural log, we can see that as the input approaches 0, the output approaches negative infinity. And so the kth term test says the series, the kth term test says if the sequence does not approach 0, then we know the series diverges. And since this is clearly not 0, we know the series of ln, an, must diverge. And that's by the kth term test. Does anyone have any questions with that? Yeah. Oh, if it was approaching from the left, well then the natural log function wouldn't be defined, right? Since the natural log is undefined for inputs that are negative, and therefore we have to take the case where it's approaching from above, from the right-hand side. Okay, that's a good question. Okay, and what was part C? So given that f of x is x minus natural log of 1 plus x is positive for x is greater than 0, determine whether that series converges or diverges. So we know that that function is positive for x is greater than 0. That means for x is greater than 0, we can rearrange and we can get x is greater than ln 1 plus x, since we know that is positive. So rearranging, we get x is greater than ln 1 plus x. Now what if we sub x equals a subscript n? Well, the left-hand side of the inequality simply just becomes a subscript n, and that's greater than the natural log of 1 plus a subscript n. And note that we're allowed to make this sub and for the inequality to hold true, because x is an, we know it's positive for all values of n. So we're actually allowed to make this sub. Now, doing that, we have an is greater than the natural log of 1 plus an, and if we take the sum of both sides, we know the series of an is going to be greater than the series in ln 1 plus an. But note that the series in an, it's given in the question, it's a convergent series. And so by the comparison test, since the series of ln of 1 plus an is less than that series, it must also converge. And that's by the comparison test. Does that make sense? Anyone got any questions? Okay. Cool. This is just a quick question. That's all right. Technical difficulties? Cool. So could someone tell me if the statement is true or false? This one should be pretty simple. Fred? Yeah, it's false. And why is it false? Yeah, exactly. So by P series, we know that if the power is greater than 1, then the series converges. And clearly 4 on 3 is greater than 1, so the series converges, and so the statement is false. Integral test. So essentially, if we have a continuous positive function that is decreasing on the interval 1 to infinity, now I'm going to stress this. This is a really important condition in order for you to use the integral test. Then we can use this test. So what this test is if the integral from 1 to infinity of the rule or the function of the sequence converges, then so does the series. And if the integral diverges, then the series also diverges. So essentially the integral and the series essentially follow the same limiting behavior. Just keep in mind, it must be decreasing on 1 to infinity. Otherwise, we can't use this test. And the ratio test is, suppose that we have an infinite series with all the terms being positive. We say that the limiting ratio between two consecutive terms is the limit as k goes to infinity of a of k plus 1 divided by a subscript k. So essentially, this is the ratio between two consecutive terms, and we're just trying to find the limiting ratio by taking the limit as k goes to infinity. And what we can deduce from this is, if r is less than 1, then the series converges. And that actually kind of makes sense, since if r is less than 1, then the magnitude of our terms are constantly getting smaller, and they'll obviously approach 0 if r is less than 1. And we said in the kth term test that if the sequence approaches 0, then convergence will happen of the series. And then conversely, if r is greater than 1, then obviously the series will diverge, since the sequence will never like steady to a single value. It'll keep getting bigger in magnitude. And if r is equal to 1, then the test is inconclusive. So we learn nothing from doing this ratio test. But good chances it'll either be less than 1 or greater than 1. So just a question. By using an appropriate test, determine whether this series converges or diverges. So can someone tell me what test we'd use for this one? Fred, do you have an answer? Yeah, so we use the ratio test here. We pretty much have two options, the ratio test and the integral test. We use the ratio test because obviously integrating this function would be quite difficult due to the exponent 2 to the n on the denominator and the n squared on the numerator. However, it would make sense to the ratio test because we have a quotient, and so if we found the ratio between two consecutive terms, obviously a bunch of the terms would cancel out. So let's try that. So let's try find the ratio r. We said that it's going to be the limit as k goes to infinity of a subscript k plus 1 on a subscript k. And that's going to be equal to limit as k goes to infinity. What would a k plus 1 be? Well, that would just be k plus 1 squared on 2 to the k plus 1. So I'm essentially just replacing n with k plus 1. And the denominator, we have a subscript k. Well, that's going to be k squared on 2 to the k. That's our denominator, that's our numerator. Now this becomes, the 2 to the k cancels out with the 2 to the k plus 1, but leaving 1, 2 on the denominator. And the numerator, we're just going to be left with k plus 1 squared. Denominator, we're going to be left with that 2 that we just spoke about, multiplied by k squared. And sorry, I forgot the limit. Now the limit as k goes to infinity, well, we can take the constant out, which is a half, and we're just left with a half limit k goes to infinity. The numerator, if we expand k plus 1 squared, becomes k squared plus 2k plus 1, all on just k squared. And when we're looking at this limiting behavior, we only care about the coefficients of the highest power of k. So we're only looking at this k squared term, this k squared term. It essentially gives us a half times 1 on 1, since that's the ratio of the coefficients, which is a half. And so our r is less than 1, and so we know the series converges using the ratio test. Okay. Next one, I'm just going to spoil it. We use the integral test. The reason for this is it should be quite clear that we can integrate this function using a u sub for u equals ln k. And doing that, we get the lower bound of 3, the upper bound of infinity, since keep in mind the lower bound of the sigma is 3 and the upper bound is infinity. The function is 1 on x ln x all squared dx. And if we let u equal ln x, well then our du is 1 on x dx. So the 1 on x and the dx become the du, and we're just left with 1 on u squared as our integrand. And the lower limit is now ln 3 instead of 3. Upper bound is still infinity, obviously. And if we evaluate this integral, we get the finite number 1 on ln 3. Since the integral gives us a finite number, it follows that the series will also give us a finite number, and therefore the series converges. Okay, now Leibniz's test for convergence. So this applies to alternating series only. It's where we're trying to find the limiting behavior of the series -1 to the k of the sequence. And what this -1 to the k is, it keeps flipping the sign. So the first term is obviously going to be positive, and then the sign is now minus a1, and then plus a2, and so on. And to test whether this alternating series converges or diverges, we use the Leibniz test. So the Leibniz test states that if these 3 conditions are satisfied, then the series converges. And the first condition is all of the terms are greater than or equal to 0. The second condition is a subscript k is greater than or equal to a subscript k plus 1 for all k. So that's essentially just saying it's non-increasing. The first one obviously was saying all terms are positive. And the last condition is the limit of the sequence equals 0. So the sequence converges to 0. And those are our 3 conditions. And if we show that all of these 3 are true, well then we've showed that the alternating series converges. Now, a series is absolutely convergent if this series is convergent. And how this relates to the alternating series? Well, if we're summing the absolute values of the sequence values, well, we only care about the sum of a0 plus, sorry, not the magnitude of a0 plus the magnitude of a1 plus so on. So we don't care about the alternating sign now. We're just evaluating the sum of the magnitudes. And if a series is absolutely convergent, it implies convergence. So once we've proved that a series has absolute convergence, we don't also need to show that it converges, since absolute convergence implies that. And if a series if a series converges, but the type of convergence is not absolute, we say it's conditionally convergent. So it's similar to like, if a series isn't convergent, it's called divergent. In this case, if a series isn't absolutely convergent, it's conditionally convergent. Determine whether that series absolutely or conditionally converges or diverges. Okay, so obviously we're going to be using Leibniz's test since we have the -1 to the n here. So there's going to be it's going to be an alternating series. So condition 1, we wanted to show that all of the terms are positive. Well, 1 on n log n is obviously going to be strictly greater than 0 for all the natural numbers, for all positive integers n, since the denominator is positive. Now, 2, we wanted to show that, I'll go back to it, we want to show that it's non-increasing, and i.e. a subscript k plus 1 is less than or equal to a subscript k. Now, what is a subscript k plus 1? So in this case, we're just replacing our n's with n plus 1s. Log n plus 1. And this is obviously going to be less than 1 on n log n, since the denominator is a lot bigger. Well, not a lot bigger, but the denominator is clearly bigger than this denominator. So our fraction is overall going to be less than 1 on n log n. And so that means our k plus 1th term is less than our kth term, and therefore the sequence is non-increasing, so condition 2 of Leibniz's test is satisfied. Now condition 3, we show that the sequence converges to 0. Well, if we take the limit as n goes to infinity of 1 on n log n, well, obviously this is going to go to 0, since the denominator is going to approach infinity. And so all 3 conditions of Leibniz's test are satisfied, and thus we show that that alternating series converges. But now we have to decide whether it has absolute or conditional convergence. And the way we're going to do that is we're going to be using the integral test. So if we integrate 1 on n log n from 2 to infinity, so note that the lower bound is 2, since the lower bound of the sum is 2. If we use the integral test, it makes sense to use the integral test since you can see that doing a u sub of u equals log n makes it easy to solve. Sorry, that should be a dn, not a dx. And the lower bound is now log 2. Computing this integral, we get an infinite number, right? This is poor notation, but we get log of infinity minus log of 2, which obviously diverges. And so since the integral diverges, we know that the series, the positive values of the series, also diverges. And therefore, it doesn't have absolute convergence, so we say it converges conditionally. Does that make sense before I move on? Okay. So Taylor series, so this is the headline of the topic. Oh, nice. Good. Nice. Oh, wait, no. It's this red thing. This one? Nice. Cool. So Taylor series, they're just infinite sums, and we use them to approximate functions near a certain x value, so x equals a. And this is the formula, which I'm assuming all of you have seen before. It's essentially an infinite polynomial in terms of x minus a, and the coefficient is given by ak equals the kth derivative of f evaluated at a divided by k factorial. So the coefficient is like the one we're usually worried about. The nth Taylor polynomial, it's literally just the Taylor series, but it stops at the nth term. So we can see that the upper bound is no longer infinity as it was in the Taylor series. The upper bound is n. And so essentially it's just the Taylor series, but it terminates at the last term, fn a on n factorial of x minus a to the n. That's the last term for the nth Taylor polynomial. The Maclaurin series, well, it's just the infinite Taylor series. However, a is 0. And so essentially it's just a series that we're approximating for around x equals 0, so around the origin. So essentially it has the exact same formula as the Taylor series, but we're just replacing a with 0. 0. Taylor's theorem states that we can approximate a function with the nth Taylor polynomial. So that's has notation p subscript n of x, so nth Taylor polynomial. And since this is obviously not equivalent to f of x, it can't be, right? Because it's not the exact same function, it's just an approximation. He says that, the Taylor's theorem says that we have to add that remainder function to account for that error we have. So it's usually called like the error function. And it has 2 forms. It has the integral form and the Lagrange form, but I don't think you'll see the integral form since it's too complex. You're only usually worried about the Lagrange form. And it's given this formula, which you're going to have to memorize, although I haven't seen it pop up in any past paper questions. And just note that c is a real number between a and x. Note that the limit as n goes to infinity of this error term approaches 0, since we have an n plus 1 factorial in the denominator, and this will shoot to infinity. So the error term goes to 0 as n gets bigger. And what this means is, if we look at Taylor's theorem, if r gets smaller as n gets bigger, then our nth Taylor polynomial becomes a better approximation for our function. So examples of Taylor series, these you should really memorize, since these are like the main ones you're going to be dealing with. I just recommend just essentially memorizing these ones. Okay. So power series. So a power series is just an infinite polynomial in terms of x minus a, with real coefficients a subscript k. So notice that this looks a lot like our Taylor series formula, and therefore it's because Taylor series is a type of power series. Convergence, divergence of a power series. So a power series, whether it converges or diverges, depends on the value of x we choose. Now, if a power series has the form, so its standard form, if it converges for all values of x on this interval, so I'll write it again down below, negative r plus a, comma r plus a. If it converges for all values of x on that interval, then we say r is the radius of convergence, and this interval is called the open interval of convergence. Since we're not using square brackets around the interval, we're using the curly brackets. Now to find what r is, it's the limiting ratio of a subscript k on a subscript k plus 1. And we're going to calculate this in the next question. And that gives us our r. And our a we can get from the power series that we're given. And I'll show you that in the next question. And essentially, the power series converges absolutely whenever the absolute value of x minus a is less than r. Now that's just saying that x is on the interval negative r plus a, comma r plus a. And obviously, when it's not in this interval, the power series will diverge. And this is for 1241 students only. So the power series can actually converge at these endpoints. So I'll just quickly finish it off. So if 1241 students only, we can actually sub in our endpoints for x, and we actually have to manually check if it converges or diverges at these endpoints.
Question 7. Find the open interval of convergence for the following power series. Now you can see that the power series we're given isn't actually in the form that we want it in, since we said the power series is defined by the sum from k equals 1 to infinity of some real coefficient times x minus a to the power of k. So the difference between what we want and what we have is that the one we're given has a coefficient of 2 before the x. Now, in order to get it into the form we want, we're going to factor out a 2 from the brackets of the numerator. And doing this, we get the series that we're given is the integral from k equals 1 to infinity. And if we take out a 2 from each bracket on the numerator, and we have k times that bracket on the numerator, we're actually going to be taking out a factor of 2 to the k. And inside, we're left with x minus 7 on 2, all to the power of k. And the denominator stays the same. It's k squared. Now we've got it in the form that we want. And note that a is equal to 7 on 2 here, since the power series is a polynomial in x minus 7 on 2. And in the standard power series formula, when we have x minus something, that something is our a. So that's why a is 7 on 2 in this case. Now all we have to do is find r. And we said r is equal to, it's the limiting ratio, as you can see above, it's the limiting ratio of two consecutive coefficients, where the coefficient of the k plus 1th term is actually on the denominator, whereas in the ratio test it was on the numerator. So on the numerator, we have the coefficient of the kth term, which is simply just 2 to the k on k squared. And on the denominator, it's the coefficient of the k plus 1th term, which would be 2 to the k plus 1 on k plus 1 squared. Okay, now simplifying the thing inside the absolute value, we get limit as k goes to infinity of, we'll get a k plus 1 squared on the numerator, and on the denominator we're left with a single 2, and then times k squared. Now we can simply factor out a half, since that's a constant, and we're left with a half times the limit as k goes to infinity, and we can also remove the absolute value sign since we know the input is positive, since it's a square over a square. The numerator is k plus 1 squared, denominator is k squared. Now we've seen this limiting quotient before in a previous question, and it's equal to 1. And if you wanted to figure out why, we're just comparing the coefficient of the highest power of k in the quotient, which is just k squared. And this gives us a half. And so our r is equal to a half, and our a is 7 on 2. And so our open interval of convergence, which we said was negative r plus a, comma r plus a. Our interval of convergence in this question is equal to negative a half plus a, which is 7 on 2, comma a half plus a, which is 7 on 2, which is equivalent to 3, comma 4. And that's our open interval of convergence for this question. Okay, now given a power series for some function f of x, we can actually manipulate the series. So we can actually get a power series for f dash of x, and we simply do that by differentiating each term in the power series. And so if we were to write that in sigma notation, our x minus a to the power of k, when we differentiate that, the k comes down to the coefficient, and our new index is k minus 1. So as you can see here. And similarly, given the power series for f of x, we can also get a power series for capital F of x, so the integral of f of x. And we simply do that by integrating the right-hand side. So we integrate each term on the right-hand side. And now our index is k plus 1. And of course, we have to divide by that coefficient. We have to divide by that new index. So that's why we have a divided by k plus 1 in our coefficient. Okay. Now just the last question. Write down the Taylor series for f of x is sine of x squared about x equals 0. Well, from one of the Taylor series that we should have memorized is about x equals 0. We know the Taylor series for sine of x is equal to x minus x cubed on 3 factorial plus x to the 5 on 5 factorial minus x to the 7 on 7 factorial plus and so on. And we can actually manipulate this known Taylor series. And since we want the Taylor series for sine of x squared, the way we're going to manipulate this one is by replacing all of our x's with x squared. And so our left-hand side becomes sine of x squared, which is what we want. And our right-hand side, well, this x becomes x squared. The x cubed on the numerator of the second term now becomes x squared cubed, which is x to the 6 on 3 factorial. And similarly, the next term will become x to the 10 on 5 factorial. Next term will become x to the 14 on 7 factorial, and so on. And that is our Taylor series for sine of x squared. Now, we could have also written this in using sigma notation if the question asked to. However, it's not necessary in this question. But if we did want to, Well, we know sine of x in sigma notation is the sum from k equals 0 to infinity of -1 to the k x to the 2k plus 1 all on k factorial. And so sine of x squared, if we were just replacing all of the x's with x squared, well, the -1 to the k stays the same. The x to the 2k plus 1 now becomes x squared to the 2k plus 1, and the denominator stays the same, k factorial. And we can simplify this. K equals 0 to infinity of -1 to the k. We could simplify our power of x to be x to the 4k plus 2 using index laws, and our denominator is still k factorial. And it also asks, state its radius of convergence. Well, we know sine of x squared converges everywhere, right? Every single value of x, sine of x squared will converge. And so the radius of convergence is infinite. Since the open interval of convergence would be -infinity to infinity.
Alrighty, let's pick up from where we left off, and we're looking at the applications of integration. Now, the first part is the average value of a function, and it states that suppose f is integrable on the closed interval a to b, then the average value of f in this interval is defined as this integral over here. So a and b are your endpoints, and plug fx in this integral and you get out your average value. Okay, so just plugging in numbers into this formula to get your average value. Now, mean value theorem for integrals says that suppose f is continuous on the closed interval a to b, then there exists a c such that this integral here, we can actually write it as f of c times b minus a. And this is pretty useful, especially when we can't find the actual value of that integral. We can just say like it's f of c times b minus a, where c is a number between a and b. And that resembles the typical mean value theorem that you would have seen in 1131 or 1141. And essentially, you just simply move the b minus a to the bottom. And that gets you like your typical mean value theorem that you see over here. All right. All right. So arc length of a curve. Now, you could be given a curve in 3 different forms. The first one is your parametric form. That's your x and y there in terms of t. You could be given it in Cartesian form. That's your usual y equals some function of x. Or you could be given it in polar form, so r equals f theta. Now, if we're given a curve in parametric form and we want to find the arc length from a to b, then to calculate that arc length, you just plug your formulas in this integral and to compute your arc length. Okay, but instead, if we're given a Cartesian form of a curve, like y equals some function of x, to find the arc length of the curve from a to b, we simply plug it into this. So take the derivative of f, square it, add 1, take the square root, and find the integral from a to b, and that gets you your arc length. Alrighty, example. So let h of x equals cosh of x, and let L be the arc length of the graph from A to B, and A is the area of the graph from x equals A to x equals B, and we want to prove that L equals A. We know that the derivative of cosh is sine, and cosh squared minus sine squared is 1. So if we plug if we plug this derivative in, oopsies. We just plug this derivative into our arc length formula, and that gives you square root 1 plus sine squared x, and we integrate that from a to b. But we know that 1 plus sine squared is cos squared, and since cos squared is positive, so we know that cos of x, that's going to be bigger than 0 for all values. And taking the square root of the squared just gets out our cos of x. Now, that's going to be our arc length from A to B. The area under the curve from A to B is simply just the integral of cos x from A to B. That's how area is defined, and therefore L equals A. All right, pretty special curve where the area under the curve equals the arc length from A to B. So this time we're looking at the arc length of a polar curve. Now, just a refresher, a polar curve is a curve where we have r equals f of theta. Now, if we have a look at an example, say like r equals e to the power theta. Theta is the angle the function makes with the positive x-axis, and r is the distance from the origin. So if we have a look at r equals e to the power theta, if we just simply plot points, say let's start from theta equals 0, we get r equals 1. So distance from the origin is 1. If we look at power 2, that's going to be on this y-axis over here. So we rotate it anti-clockwise by power 2. We get the r equals e to the power 2. That's going to be the distance from the origin. Same with e to the power pi. We get something like this, e to the power pi. E to the power 3 pi on 2. That's going to be like somewhere over here, and then e to the power 2 pi. It's going to be somewhere over there. Notice that e is always increasing. So as we keep increasing that theta, our distance from the origin is going to keep increasing, and we get a curve something like this. It's bigger, bigger, bigger. It's bigger, and essentially loops back. If you want to have angles larger than 2 pi, it just keeps going around in spirals. Alrighty, and that L equals the integral from theta 0 to theta 1 of that square root. That gets you the arc length of a polar curve. Alrighty, last part is the surface area. And suppose we have a curve C that is simple and lies above or on the x-axis. Now, when we rotate that around the x-axis, we're going to have a surface area that's produced. And again, 3 different forms. One's parametric, Cartesian, and polar. First one here, that's going to be the parametric form. And to compute the surface area around the x-axis, we're going to use this first formula over here. The second one is if you're given a curve in Cartesian form. And the third one is if you're given it in polar form. And notice that they resemble your arc length formulas really nicely. So just remembering a set either arc length or surface area formulas, and you should easily know the other counterpart. The question here, we have a equation y equals r on hx. And we're going to use calculus to show that the surface area S of the curve is given by S equals pi r times square root r squared plus h squared. Now, this is given in Cartesian form, so we're going to bring out the Cartesian formula for surface area. And so we're just going to plug in y outside, so 2 pi times y. And then notice that the derivative of y is going to be y dash equals on H. And that derivative, we plug this inside here, square root it, add 1, square it, add 1, and then take the square root, and that gets our formula. So again, just combining the constants out in the process of integration. We're just taking this H out, H to the outside, just to make our integration easier. And so in the end, once we pull out all the constants, we end up with the integral of x from 0 to h. And we all know how to integrate x. That's really easy. We get x squared on 2 bounded from 0 to h. Plug your numbers in. We get h squared on 2 times our initial constant. And then our h squared here cancels h squared, 2 and 2 cancels on the top. And then in the end, we get pi r times square root r squared plus h squared. And that is exactly what we're trying to prove. Alrighty. Now, a special gift, we've recently released a revision sheet for 1231/1241 that summarizes most of the important formulas that you'll encounter in the course. So definitely scan this QR code and download that sheet. It'll be really helpful. Along with other revision sheets for like 1131 and 1141, and also MathSoc. But yeah, that's it. Definitely, if you have any feedback, please scan this QR code. Any positive, negative, any feedback is appreciated. And yeah, thank you all for watching this calculus revision seminar. And yeah, we wish you all the best for your exams.